So what do we infer from this? We infer that there may be a very small effect from extra CO2 in the atmosphere, but it cannot be anything like as big as the models are predicting. So we now move on then to why are the models getting things wrong and predicting disaster? Here is one reason why models fail. Now, in mathematics, you can often find absolute proof. Here is a proof without words by me of, I don't say it's original, but I think it's by me, of Pythagoras' theorem. Here you have an irregular pentagon, and it contains within it either the squares of the two short sides and two of the right triangles we're looking at, or it contains the square on the hypotenuse and two triangles. That is an absolute, rigorous, complete proof of Pythagoras' theorem. Now, what the heck's Pythagoras' theorem got to do with global warming? Well, it's this, that in the physical sciences generally, and in particular in something like climate science, where the data we have are largely inadequate, there just isn't enough of it, you can't make absolute proofs most of the time. Here is a formidable atmospheric physicist from Japan, Shunichi Akasofu. No supercomputer, no matter how powerful, is able to prove definitively a simplistic hypothesis that says the greenhouse effect is responsible for warming. It can't be done. So we now have to look at another equation. There we are. This one you'll all have known about. This is Einstein's equation. And now let's just magic it away and put another equation in its place. Broadly similar. You've still got radiant energy in watts per square meter on the left, but now you have emissivity, you have a constant, and you have temperature to the power of 4. Now this is the Stefan-Boltzmann equation. And the importance of this equation is that it tells you that there is a formula that links the extra radiant energy that might arise from radiative forcings, like putting more CO2 in the atmosphere, and temperature. But you notice that the temperature is to the 4th power, which means that if you have an increase in radiant energy, the increase in temperature is actually going to be very small. And as a result, we can now look at a table of the different values for how much we might expect temperature to change that are available in the scientific literature. And you'll see it's a very huge range. Here's my own calculation, and we get 1.6 degrees Celsius as the change in temperature for a doubling of CO2. Now, the IPCC says 3 Celsius, about twice what I make it to be. And one of the things that's been said to me over and over again by the conformists is, oh yes, but the science of this has been settled for 100 years. It was Arrhenius who did the first calculations in his paper of 1896, and he said it was somewhere between 4 and 8 Celsius for a doubling of CO2, and the Stern report says 11, and so how dare you say only 1.6? But you see, I don't just read English, I also read German. And in 1906, Arrhenius, having the Stefan-Boltzmann equation available to him, which he hadn't quite got hold of in his first paper, recalculated everything. And he came to the same conclusion as I had, that for a doubling of CO2 concentration, you will get 1.6 Celsius of temperature change. And this is the range of temperature that is there. So why so wide a range? Maybe because we really don't know how much CO2 there is effect on temperature. And we're now going to look at some of the constraints that limit the effect which CO2 can have. First of all, here is its percentage by volume in the atmosphere. It did occupy 0.03% of the atmosphere in 1750. It now occupies, getting on for 0.04%, and that gives you a change of 1/10,000th part of the atmosphere more now than in 1750 is occupied by CO2. Now that in itself is a rather simplistic analysis, so we're going to go a little further. The IPCC has constantly rethought how much it thinks CO2 influences temperature. And in that forcing formula that I showed you before, the coefficient Z, it was 6.4 in 1995, it was 5.35 in 2001. They no longer publish it, but I've managed to calculate it from the data they have provided. It's 5.27 now. So it's come down by nearly 20% in just 12 years. Equivalent, if you like, to a 20% reduction in the entire greenhouse gas emissions of the world in only 12 years. So the consensus does not agree with itself. And the most extraordinary thing is that the IPCC, notwithstanding these reductions, and many other reductions I could point to, has maintained its best central estimate of climate sensitivity at 3 degrees Celsius in response to a doubling of CO2 throughout. None of this has been recalculated properly. I don't think we're getting this honest science. So if we move quickly on then to the next slide, here we get a rather prodigious mismatch again between CO2 concentration, which is the black line, and temperature concentration, which is the blue line, going right back to almost 600,000 years into the past. And here we had almost 7,000 parts per million of CO2 compared with 385 or thereby today. 7,000 then. Temperature managed to get up to about 22 Celsius and has never really gone much higher than that at any time over the past 500 million years. As best it can be reconstructed. There are, of course, again, difficulties going that far and getting accurate results, but the IPCC itself says that in the Cambrian, carbon dioxide certainly went up, in its opinion, to around 6,000 parts per million, so this is not a controversial graph. What it is controversial is that, again, it doesn't show a terribly good link between the two, and it doesn't show, in particular, the runaway climate change when we had a lot of carbon dioxide in the atmosphere that the Tory party has written about in one of the most scientifically illiterate considerations of climate change that I've ever had the misfortune to have to read. So we then go on to look at this logarithmic effect that the first 20 parts per million of CO2 have a very much greater effect, not probably quite as much greater as is shown here, than all the remaining 400 that follow it. So every time we put more CO2 in the atmosphere, it has less effect than it had before. Then we come on to a problem of how long does it stay in the atmosphere once we've put it there. Now the answer is it's around 5 to 10 years, best estimate around 7 years. Here are a couple of dozen papers. Let's have another look, let's have some more of these. You see plenty of references there. But bingo, the IPCC says, oh no, let's call it 50 to 200 years. What they've done is to produce a weaselly definition of what the atmospheric residence time is. Now, to you and me, being simple, unscientific folk, we think we burn something and so we create some carbon dioxide and up it goes into the atmosphere. There's a molecule. How long, on average, does it stay in the atmosphere? And they don't define it that way. They say, well, it's the time required for the atmosphere to adjust to a future equilibrium state if emissions change abruptly. That's got nothing to do with any definition of residence time that any respectable scientist would recognize. And they have been widely criticized for adhering, ever since 1990, to this perfectly ludicrous definition, which is not in the least bit helpful in trying to work out what effect CO2 will really have. So we now summarize this by saying that there are some quite powerful constraints on how much impact CO2 can have. There's very little additional CO2 in the atmosphere. CO2 has only a few principal absorption bands, the most important of which for these purposes is probably the one at 14.99 microns. At the surface, water vapor dominates CO2. We've already seen that one effect of that. It's only further up that you get any warming effect at all, and that's why its effect diminishes logarithmically the more you put into the atmosphere. CO2 is not particularly potent. It's only 1/23 as potent as methane, for instance. There's no tropical mid-troposphere hotspot. We saw that. Its atmospheric residence time is short, 5 to 10 years, whatever the UN says, and CO2 correlates very poorly with temperature, both in our own time and, of course, going all the way back 500 million years. Quite powerful constraints on what CO2 can achieve. We have to try and work out what effect can it have on the climate. And here we're going to wander into territory where all kind of reason departs. And here we have Al Gore in An Inconvenient Truth. And we're going to look at just a few of the fantastically interesting errors in his film. He says there is one relationship that's more powerful than all the others, and it is this: when there's more carbon dioxide, the temperature gets warmer because it traps more heat from the sun inside. And what he's trying to do there is to suggest that in the former climate, when we weren't adding much CO2 to the atmosphere, it was the CO2 that was changing, and that was causing the changes of temperature that led to the beginning and ending of the ice ages. That's the order of precedence which he gives. It is almost unanimous in the scientific peer-reviewed literature that that is not the case. Here is Petit et al., 1999. Here's CO2 concentration and here's temperature. They appear to track very nicely together. But if you look at them closely enough, it is actually the temperature that changes first by somewhere between 800 and 2,800 years, depending on which paper you read, and the CO2 which follows. Let's go on to the next one. Now, one of the problems we've seen is that correlation doesn't always imply causation, and it didn't in Gore's case, because here we've got sunspot number on the bottom and the number of Republican senators in the US Senate. There's a beautiful correlation there. I think you'll have to accept that I have now, actually it was Douglas Keenan, a friend of mine, who has identified a really important climatic result.